Okay, so if we go back here to the new candidate selection algorithm, we have most of this done except for the originality and similarity. So the goal of this improvement is to essentially compare each new idea to all of the ideas that were published in the last, say, 60 days, and then make sure that we don't publish an idea that's too similar to one of those. We'll do that with a multiplier again, but how we get there is a little bit more tricky because now we need to actually compare, how close one idea is to another idea semantically. And to do that, we need something that's called embeddings. So I'm not an ML expert by any stretch, but the good news is also that we don't need to deeply understand the low-level concepts in order to be able to apply them for our use cases. I'll try to explain it at least at a high level, though. So an embedding is a way to turn some sort of text, usually text. You can actually also generate embeddings for images and videos and audio. But in our case, it's a way to turn text into a vector that represents kind of the semantics, right? What that text is about. Those vectors can have different sizes depending on how much detail you want. A size that's sufficient for us, and that's pretty typical for use cases like this, is 768 dimensions. So if we have this text here, AI-powered fintech for gig workers, right? That might be like a high-level description of an idea. And it might end up looking like this in vector form. So we just have numbers here between -1 and +1 and 768 of those. And that represents this text. And that's called an embedding. And then what we do with those is when we have embeddings for two different texts, we can now compare them using, there's a lot of different ways to compare them, but the one that we're going to be using is called cosine similarity. So cosine similarity tells us how similar two ideas are by essentially comparing the direction of the vectors. So if the direction is pretty similar, regardless of the magnitude of the vector, then the ideas are considered pretty similar. So here's sort of a very simplified 2D example, right? So you might have some terms here, like some financial terms, fintech, payments, banking app, and probably the similarity between fintech and banking app might be fairly high. So maybe it's something like 0.82. And then we have restaurant app and neobank. Those are pretty different concepts, right? There's almost no similarity. So this might return something like 0.15. Payments and food delivery, right, are somewhat related because usually payments is like an aspect of a delivery app like that. A restaurant app is probably pretty close to a food delivery. Anyway, so there's sort of a high-level visualization. But again, we're going to be dealing with much more complex vectors. So what are we going to do with these calculations? So essentially, for each of the candidates in the pool that we're considering developing into a business model, we're going to be calculating how similar they are to any of the ideas that were published in the last 60 days. And we'll figure out what's the maximum similarity, right? What's the closest idea that we already published, and then essentially calculate a penalty based on that. So if the maximum similarity for a candidate is 1.0, that means that it's identical, right? It's pretty much exactly the same. And that puts it here firmly in this so-called kill zone. So the multiplier is going to be 0. It's going to get a score of 0 in the end. And we'll figure out exactly where this cutoff is, this threshold. I put 0.85 in here as a placeholder. We'll actually figure out our real thresholds. So these might be reasonable starting points. But that's the idea, right? So if the similarity is between 0.85 and 1, we'll just dismiss this idea completely. And then on the other side, if it's between 0 and, say, 0.7, and again, we'll figure out what the right number there is. Then we consider it safe, so we don't ding it at all. There's no negative multiplier. It just gets a 1.0. And then the most interesting section is the one in the middle. So that's kind of our penalty region between maybe something like 0.7 and 0.85. We'll calculate a penalty here that's essentially a linear decay, right? So something at the 0.7 mark would get no penalty, so that would be a 1. And then something at the 0.85 mark would be a 0. And then everything in between would be somewhere between 1 and 0. So just sort of a linear interpolation. Now, before we can do any of this, we actually need a place to store these embeddings, these vectors. And traditional relational databases aren't well suited for this task. So what we're going to do instead is use a vector database called ChromaDB. Just like SQLite, this is just a local file-based database. This is very easy to use for the purpose of our course. In production, I actually use a PostgreSQL extension called pgvector, but the principle is identical. So you might pick pgvector in production, but ChromaDB is perfect for our purpose here. So in our first prompt, we'll add ChromaDB and calculate the embeddings using a special embedding model. This is going to be another Gemini model. We will use Gemini embedding 001. That's the most recent non-preview model. They actually just released Gemini embedding 002 preview. And the main difference between this and the previous one is that the new model adds multimodal support. So you can create embeddings for not just text, but also for images, video files, audio, and PDF files. But we don't need any of that. So we'll stick with the non-preview model 001.